In this lesson, we'll derive the product and quotient rules for differentiation. The derivative is defined as shown here, where we have the rise is the difference in the y values at those 2 points where we have x and x plus h. That's the rise, and the run is h, the difference in the x values. We want to take that so that h becomes closer and closer to 0, and that gives us the derivative, which of course just simply gives us the slope of the tangent line. In the last lesson, we had the derivative of a polynomial x to the n is shown there. The derivative of sine was cosine, the derivative of cosine was negative sine, and the derivative of the exponential is the exponential function itself. Now I'll derive the product rule for you here. You don't have to memorize this derivation, but we are interested in the result, so we'll need to see where it comes from. So we have two functions here of x, one we'll call u of x and the other one v of x, that we're multiplying together. And so by the definition of the derivative, we take the function at x plus h, we'll work out the y value there, which is the product of those two functions. We'll subtract the y value at x and divide by the h. And we want to work that out as h approaches 0. Now what we'll do is we'll subtract and add a u of x plus h times a v of x in the numerator. So adding and subtracting it, of course, doesn't change the value of that whole thing. And so we have our original function there is given in that part, and we've subtracted a u of x plus h times a v of x, and we've added that same thing there. So we've subtracted and added, which means that we're really changing nothing. And the last part is, of course, the part of the original limit there, so that's still there. Now, the reason we subtracted and added that was to rearrange what we have. And so here we have a u of x plus h as a common factor, leaving us with a v of x plus h there, and a v of x there that we're subtracting. All of that is over h. We'll separate that out from the last two terms there, and we'll take a v of x this time as a common factor. And so we'll take that out there, and we're left with a u of x plus h there, minus a u of x, again all over h. Now we did that so that we can separate these out. So this part over here is sitting there, and this part over here is sitting over here. We've got the limit of that times that is the same as taking the limit of the individual ones and then multiplying them. And similarly, on the second term there, we've got a limit of this times this. So we can see that the last term there is the limit of that last term. And we've got a v of x that we've taken out of the limit, and we can do that because there is no h in the v of x. So as h approaches 0, v of x will be just v of x. It's not affected by what h is doing. And so what we have here now is the product of this thing here. Now as h approaches 0, that just becomes a u of x. And this is, of course, the definition of the derivative of v of x. So that's v dashed x, we'll write that for the derivative. Here we have a v of x. And this part over here we have the derivative of u of x. So our product rule there tells us that when we have the derivative of the product of two functions, both of x, then what we do is we take the first function, multiply it by the derivative of the second function, so we can write it more briefly like this, plus the second function times the derivative of the first. So we can write it either as written there in the box, or as in the line above it. That's the product rule. Product rule because we're multiplying two functions there, and we get the first function times the derivative of the second plus the second function times the derivative of the first. Let's have a look at an example of that. So we have the product of two functions here. We have 2x cubed and we've got sine x. So the first thing we've got to do is identify those two functions. Call the first one u and the second one v. Then we can apply the product rule straight off. Now the derivative of u is just 6x squared, and the derivative of v is just cosine x. So applying the product rule now, we have the first function u, which is 2x cubed, multiplied by the derivative of the second function, which of course is our cosine x. And to that we add the v, which is of course the sine x, and we multiply that by the derivative of the first function, which is our 6x squared. And that's as far as we can go with that. Let's now derive the quotient rule. The derivative of a function is the value of the function at x plus h, and in this case the function is of course the quotient of two functions u and v, minus the value of the function at x divided by the h as the h gets smaller and smaller and smaller. We'll simplify the value inside the limit there. We'll get a common denominator of the h times the v of x plus h times the v of x. So the u of x plus h needs to be multiplied by the v of x. That's the first term. And the second term, u of x, is multiplied by the v of x plus h, all divided by h, and the common denominator there of v of x plus h times v of x. Now, like before, we'll subtract and add a term, in this case u times v, so that we can rearrange the whole thing. So we're subtracting firstly a u of x times v of x and adding it, and the rest is the same as it was above. So we'll gather up the first two terms and we'll take a v of x out as a common factor, leaving us with a u of x plus h minus a u of x. Now all of that's going to be over the h. We'll borrow that from the denominator and leave the v of x plus h times the v of x down the bottom there. And the last two terms there will take a u of x out as a common factor, leaving us with a v of x there and a v of x plus h there. Now we've also taken a negative sign out, which seems to complicate the issue, but does simplify later on. So taking the negative out there, we've got the v of x plus h is negative, and then to make this positive we'll need a negative there. Negative times that negative will make it a positive v of x times a u of x. So we have equivalent terms there. Now we've got to deal with the limits, and when we've got products and quotients and we're taking the limit of those products and quotients, we can actually do the products of the limits. So looking at this first term here, we can take the limit of the whole thing. Now the v of x doesn't have a h in it, so that doesn't need to be inside the limit. This one is inside the limit there, so that's that term there. And likewise the u of x doesn't need to be in the limit, but the other term does. And the denominator also has a h there, so we do need to take the limit of that as well. And we can simplify that down a little bit, because the limit as h approaches 0 of that term there is of course just the derivative of the function u. So we can write that as a v of x times the derivative of u. So that's that term there. And this one here becomes a u of x, or just u, and the second term is of course the derivative of v, so that's the dv dx. And down the bottom over here we've got h approaching to 0, so that'll just be a v of x. So we've got a v of x times a v of x is just the v squared. So note that the form of this here is that we've got the denominator first and then minus the numerator, and then we've got the derivatives of the other part of that quotient next to them. So let's have a look at an example. Now in this first example, I've put this in so that you can see that you shouldn't always just jump into the quotient rule when you have two functions being divided. So in this example here, we've got a numerator function and a denominator function, but it's much easier just simply to divide through by x. So that's what we'll do firstly with the f of x. So x into the 3x squared will just give us a 3x. And this of course is x to the half divided by x to the 1, so we'll get an x to the negative a half. And we can differentiate that straight off to get our 3 plus a negative a half times 2x to the minus 1.5. And that is a lot easier than using the quotient rule. In this example, we will use the quotient rule to differentiate tan of x. Now tan is the same as sine over cosine, and so we have a good candidate here for the quotient rule. We'll put u as sine x and v as cosine x so that we can apply the quotient rule here. So now all we've got to do is differentiate the u and the v, of course, and put all those values in. So we've got the v is cosine x, that's our denominator, and we need to differentiate the u, which is the sine x. And we then have our u, which is the numerator, sine x, times the derivative of the denominator cosine x. And all of that's over the v squared, the denominator squared. So now going through and calculating those derivatives, the derivative of sine is cosine, and the derivative of cosine is minus sine. So now we have a cosine squared minus, and a minus is plus, so cosine squared plus sine squared is equal to 1. We get 1 over cosine squared is the derivative of tan x. And that's an important result, so we'll put that on our formula sheet. The derivative of tan x is 1 over cosine squared x. 1 over cosine can also be written as secant or sec of x, so you'll see that written also as sec squared x. In this example, we're asked for the gradient of the tangent of the function as given there at a particular point. So to get the gradient, we need to differentiate the function. The function is the quotient of two functions, so we can use the quotient rule, and then we need to evaluate it at that given point. So our numerator will make u, and our denominator will make v. So then we can apply the quotient rule directly and put our v's and u's in. Our v is our 1 plus x squared, and we want to differentiate the u, which is of course 1 plus sine x, and the u is 1 plus sine x, and we want to differentiate the v. And the denominator is v squared. So going ahead with those differentiations then, we've got our 1 plus x squared there still, and the derivative of 1 is 0, and the derivative of sine is cosine. And we're subtracting that first term times the derivative of this, and again the derivative of 1 is 0, and that'll give us a 2x. So then we can expand those out and simplify, but we can actually work those out for the specific point where x equals 0. So we can do that, and then that makes the algebra a little bit easier. So 0 for x gives us a 0 there. We're working out cosine of 0, sine of 0, and that's 0. So, and the 0, of course, for x in the denominator as well. Okay, so we're going to get cosine of 0 is 1. And so that's a 1 times a 1 is 1. And all of this doesn't matter what sine of 0 is. It is 0, but we're multiplying it there by 0, so that'll all drop out to 0. And the denominator there is just 1 squared is 1. So our final answer is, of course, just 1. So we've seen how the product rule is derived. And the product rule is, of course, the first function times the derivative of the second, plus the second function times the derivative of the first. And we've also seen the derivation of the quotient rule, which says that we have the denominator function times the derivative of the numerator, minus that the other way around, the numerator times the derivative of the denominator, all over the denominator squared.